Good afternoon, students. Let us start today's class on analog electronic circuits. I had already discussed this particular module by showing you the textbook. Now, today I am showing you my PowerPoint, only a few slides in the beginning, then I will go back to the textbook only. So, the name of this module is Feedback and Oscillator Circuits. First, let us see the types of amplifiers. Amplifiers can be classified as many types based on their functionality, based on their operation, and based on their application as well. Here I am briefly discussing only 4 types of amplifiers as per their basic configuration. You can see on the screen, the first type is called as voltage amplifier and the second type is called as current amplifier. In the first type, you can see that voltage is the input and voltage itself is the output. So it is called as voltage amplifier. Now the second type is called current amplifier, where current itself is the input and current itself is the output. In electronics, we will have many applications where sometimes we want the voltage to be boosted and sometimes we want the current to be boosted. For example, in one of my previous classes, I had asked you, when the symbol of the amplifier is a triangle symbol, if it is used in the digital circuits, what is it called? It is called as buffer. Now, buffer is also an amplifier, but it is not a voltage amplifier. It is a current amplifier where it will increase the current level of the input signal. Similarly, the voltage amplifier will increase the voltage level of the input signal. In addition, later on, we will have a separate class called power amplifiers. That means we are going to discuss power amplifiers in module 5. Let me not discuss power amplifiers here now. Power amplifiers are basically voltage as well as current together. Then they are called power amplifiers. So, till now we have been discussing only about the small signal amplifiers. Now, whatever amplifiers right now I am discussing also come under small signal only. So, you can see a voltage amplifier and a current amplifier. Then you can also see in the next slide transconductance amplifier and transresistance amplifier. You can see the difference here in transconductance amplifier where the input is voltage and output is current. Whereas in a transresistance amplifier, the input is current and the output is voltage. In other words, the transconductance amplifier is also called as voltage to current converter and the transresistance amplifier is also called as current to voltage converter. As I have been telling you earlier also, you will be studying one subject called linear integrated circuits in the next semester, where you will understand how an operational amplifier can be used as a current to voltage converter or a voltage to current converter. Because at times we have some applications where input signals voltage has to be converted into current at the output. Or at times the input signals current needs to be converted into voltage at the output. So in such cases, we are going to use transconductance amplifier and transresistance amplifier. So we have seen basically 4 types of amplifiers. One is voltage amplifier, then current amplifier, then transconductance amplifier, then transresistance amplifier. Now why I am discussing these 4 types basically is, we are not going to go into a deeper design of these 4 types. The purpose of discussing these 4 types is because later on, as we are going to discuss the feedback connection types, we had seen yesterday about voltage series feedback, voltage shunt feedback, current series feedback and current shunt feedback. Now, the performance of all these 4 types of amplifiers can be increased by using those 4 types of feedback connections. Now understand, we are discussing 4 types of amplifiers: voltage amplifier, current amplifier, transconductance amplifier, transresistance amplifier. Now the performance of these 4 types of amplifiers can be improvised by using additionally those 4 feedback connection types. That is voltage series feedback, voltage shunt feedback, current series feedback, current shunt feedback, based on the particular application. You can see that in the circuits which I am right now showing you, there is no feedback at all. Now we are discussing about the effect of negative feedback. So I thought let me show you these four pictures of four types of amplifiers. Now let me discuss a little more basics about the negative feedback which I had already discussed in the previous class. Still let me show you some equations which are part of the basics for negative feedback. Let me go to the next slide now. So you are already familiar with this particular block where we have a basic amplifier with gain A. Then we have a sampling network at the output. Through the sampling network, we take a portion of the output back to a feedback network. Now from the feedback network, we take that feedback back to a mixer network where the signal will be mixed with the input signal. And then it will be fed back to the basic amplifier. So you can see that Vs plus or minus Vf is equal to Vd. That means there will be a differential input here. That difference is equal to Vs plus Vf or Vs minus Vf, depending upon whether we are applying positive feedback or negative feedback. This is the block diagram of a feedback amplifier. And I had discussed this yesterday in detail about how voltage is taken back or how current is taken back and how it is connected in series or how it is connected in shunt at the input side. So you are already familiar with the basic block diagram of a feedback amplifier. I want to tell you one more thing now, that this gain A is generally called as an open loop gain. That means if the feedback is not there, then only the amplifier will be working, then it is called as open loop gain. Now when we apply feedback, the gain is going to change. We will see that now in the next slide. Okay, before discussing the gain, I had also shown you how to sample the voltage yesterday. Now there is a point here, when we sample the voltage from the output, now this is called voltage sampling back to the feedback network. Now the requirement here is that the input impedance of the feedback network must be much greater than the load resistance. Otherwise what may happen? Whatever current is going to the load, it will get diverted to the feedback network also. If the input impedance of the feedback network is lesser, then we will have unnecessarily wastage of power. Actually the amplifier's output should be supplied only to the load, and we are connecting the feedback for getting some other advantages as the linear response, as the increased frequency response, as the increased input impedance, as the reduced output impedance, as we had seen in yesterday's class. That is the purpose of applying negative feedback. But in effect, if the feedback network's input impedance is lesser, then the power will be unnecessarily wasted. So the requirement here while sampling the voltage is that input impedance of the feedback network must be much greater than the load resistance. That is how we have to design the feedback network. This is as far as sampling the voltage is concerned. Now as far as sampling the current is concerned, you can see the current goes to the load, then it goes to the feedback network, then it comes back to the basic amplifier because that's a ground connection or return connection. Now here the requirement is that input impedance of the feedback network must be much smaller than the load resistance. Why? Obviously here there is a series resistance here. Along with the load, you will have a series resistance at the input side of the feedback network. Now this should be much smaller. The reason is, as I told already in the previous slide, all the power has to be supplied to load resistance only. So in such a case where we are sampling current, the input impedance of the feedback network is much smaller. So when we are sampling the current, the feedback network will change. When we are sampling the voltage, the feedback network will change, which means the same feedback network cannot be used with all types of feedback connections. Okay. So I wanted to tell you all these basics to some extent. before proceeding further. Now let us go to one more basics of how to derive an expression for the closed loop gain. Later on, let me discuss again from the textbook about the feedback connection types. Again, we had seen yesterday how to have a series connection at the input or series feedback at the input. You can see the feedback's output is connected in series with the input circuitry. Similarly, how a shunt connection can be made, that also can be seen. And yesterday I had told you why there is this current source whenever there is a shunt connection. I had shown two voltage sources in parallel and I told you the complications there. Two voltage sources with the different voltages cannot be in parallel at all. That's why this has to be a current source now. For this purpose only, I discussed the basic four types of amplifiers called voltage amplifier, current amplifier, trans resistance amplifier, trans conductance amplifier. Now naturally, those four will have different types of combinations of these four feedback types, so as to have an improvisation in their performance. Okay, now let me proceed with the basic derivation of a negative feedback amplifier. You can see in the picture that the AOL is mentioned. AOL stands for open loop gain. And you can see that the signal from the source is given the symbol Vs, and the signal which is input to the amplifier is called as Vi, because there will be a difference now. Output signal is called V0, and portion of the V0 is given to the feedback network. This beta is a fraction, as I had mentioned in yesterday's class. Beta will be always less than unity because a small portion of the output is taken back to the input. Now you can see there is a negative sign here, which means this is specifically a negative feedback. In the beginning now we are discussing only negative feedback. Later on we will go for discussion of positive feedback. As we have seen yesterday, the disadvantage with the negative feedback is only one, that is the gain will be reduced. But the advantages of the negative feedback will be 6. That is why we are discussing the negative feedback now. So you can see Vf is the notation given for the feedback signal. So now we know that V0 by Vi is this AOL or open loop gain. And Vf is equal to beta into V0, where beta is a number less than unity. And we know that Vi equals Vs minus Vf, because it's a negative feedback. Now using these equations, let us find out the expression for the closed loop gain now. So we know that Vi is Vs minus Vf, and Vf is beta into V0. And closed loop gain ACL is V0 divided by Vs, because with the closed loop, input to the whole system is given as Vs, output from the system is taken as V0. So naturally closed loop gain is V0 by Vs, whereas the open loop gain was V0 by Vi. Now let us derive an expression for the closed loop gain. Therefore, ACL is what is V0? V0 is A into Vi. I am simply writing A here instead of AOL, because in future whenever we mention capital A, that means open loop gain. We need not keep on writing AOL everywhere. In general, for any amplifier we signify the gain as capital A and we signify the feedback as small beta. Okay, and whenever we have this closed loop gain, either we write ACL or we also write AF also. AF basically stands for gain with feedback. So that way now ACL is A into Vi divided by Vi plus Vf. Why? V0 is A into Vi. Vs is what? Vi plus Vf. You can see here Vs is Vi plus Vf, or Vi is Vs minus Vf. Okay. Now ACL is A into Vi divided by Vi plus Vf. Let us substitute for Vf now, because we know that Vf is beta into V naught. So ACL is A into Vi divided by Vi plus beta V naught. Okay. Now let's substitute for V naught also in terms of Vi, because V naught we know that is V naught is nothing but A into Vi. So now closed loop gain is A into Vi divided by Vi plus beta into A into Vi, because V naught is nothing but A into Vi. So now you can see Vi is at the numerator also, Vi is commonly there at the denominator also. So if Vi gets cancelled, what will be the next equation for the closed loop gain? Can anybody tell me? Just observing this last equation, what will be the net expression for ACL? Can anybody tell me? No one is telling. It is actually very simple. Let me show you. See, we will be writing an equation called AF equals A by 1 plus beta into A. You can see here, ACL is nothing but AF. AF means gain with feedback. A is now gain without feedback. So we can see Vi gets cancelled and we have AF equals A by 1 plus beta into A. Sometimes we call it as A by 1 plus A beta also. And we call it as AF also, ACL also. Both are one and the same. Now you can look at this equation. This is the equation for the closed loop gain, which means with the negative feedback, we have a reduction in gain. You can see A is a value, beta is a fraction, A is a larger value, beta is a small fraction. For example, let us say, take an example of A equals 100 and take a fraction of beta equals 0.1. Now, what it becomes is A is 100, this beta is 0.1, 0.1 into 100 is 10. So the feedback factor, feedback gain with the feedback happens 100 divided by 11. Approximately, it becomes 100 by 10. If we ignore this 1, it becomes 100 by 10, and that 100 by 10 gradually becomes 10. Which means if the open loop gain was 100, the closed loop gain will be 10. It will be reduced that much. So based on the requirement of the application, we will have to choose the value of beta. Here I told you that beta can be 0.1. Beta can be 0.01 also. It can be 0.001 also. It can be 10% also. It can be 1% also. Right? It can be 0.1% also. That depends on the particular application. So A will be naturally larger, beta can be smaller. Now let us say if this A beta is much larger than 1, the product of beta and A, if it is much larger than 1. For example, let us say A is 1000 and beta is, let us say 0.1. A is 1000 and beta is 0.1. Then A into beta will be 1000 into 0.1 is 100. When compared to 100, this 1 can be reduced or ignored. The 1 can be ignored. Then this becomes 1000 by 100. Or we can simply say, if the value of A beta is much larger, then the 1 can be ignored. Then A by A beta will become 1 by beta only. Which means, for any closed loop system of amplifier with the negative feedback, if this factor A beta is much larger, then the feedback gain will be 1 over beta. That's all. Now what is the conclusion there? With the negative feedback, if let us say if the A beta is much larger compared to unity, then AF will become A by A beta, that is 1 by beta. That means if the A beta is much larger, then the gain with the feedback will be independent of the open loop gain itself. That means even A will not be considered for the closed loop gain, provided A beta is much larger. So in such a case, the factor A beta is called as the loop gain. This particular factor A into beta, if it is much larger, then the feedback gain will be just 1 over beta. Therefore, this particular factor A beta is called as loop gain. But if this A beta is not much larger, then we cannot ignore this unity also. If A beta is smaller, then we cannot ignore the unity also. That one has to be considered along with A beta. That is why, depending upon a specific application, open loop gain will be known for the amplifier, beta will be chosen for the specific application. Okay. So now you are familiar with the particular term called AF equals A by 1 plus A beta. Let me stop sharing PowerPoint now because I am going to start discussing the textbook again. Let me stop sharing this. I wanted that let these basics be discussed first before going for the derivations of the equations for the feedback types, the 4 types which we had discussed earlier. So let me stop sharing this PPT. Let me start sharing the textbooks page. Okay, now you can see the textbooks page and you are seeing the 4 feedback connection types. That is, first one is voltage and series feedback, then voltage and shunt feedback, then current and series feedback, and current and shunt feedback. These 4 I had shown you yesterday. So let me proceed now. I want to elaborate on this particular table now. Okay, you can see this particular table that I am showing you on the screen. So in the textbook he says, in this section we examine the gain of each of the feedback circuit connections of the earlier figure. The gain without feedback A is that of the amplifier stage. With the feedback beta, the overall gain of the circuit is reduced by a factor of 1 plus beta A as detailed below. He is saying it is as detailed below. But I have already shown you that particular derivation now. So the overall gain is reduced by a factor of 1 plus beta A. Why? Because this 1 plus beta A came in the denominator. That is how we had seen that equation, AF equals A by 1 plus A beta. So now a summary of the gain, feedback factor and gain with feedback is provided for reference in table 14.1. That is the table shown here. Now for voltage series, the gain without feedback is V0 by Vi. For voltage shunt, it is V0 by Ii. For current series, it is I0 by Vi. Current shunt, it is I0 by Ii. You'll have to recall those 4 diagrams which I had shown you yesterday in a larger size. Today I have shown you in a smaller size. And I had shown you that voltage series, voltage shunt connections in my PowerPoint slide also. Please recall all that. This gain without feedback is referred to those particular terms. Now feedback or beta with voltage series is Vf by V0. In case of voltage shunt, it is If by V0 because it is voltage shunt. So we are choosing the current source there at the input, as I had told you already yesterday. In case of current series, it is Vs by I0, and in case of current shunt, it is If by I0. Let me admit the student. Okay, finally we are seeing the gain with feedback, AF is V0 by Vs, V0 by Is, I0 by Vs, I0 by Is as per the diagrams. Now, when I go for the next derivations, you'll have to keep on visualizing those diagrams. Okay. Anyway, I'll be sharing my PowerPoint also later on in the Google class. But I'll be doing that after I complete this particular discussion. Let me proceed now. Let us go for this voltage series feedback and let us see its derivation now. See, even in the voltage series feedback, we are going to arrive at the same equation which I showed you earlier. That figure 14.2a, you have to recall that figure now. If there is no feedback, the voltage gain of the amplifier is A equals V0 by Vs. When there is no feedback, Vs is equal to Vi. So it will be V0 by Vi. Now, if a feedback signal Vf is connected in series with the input, then Vi equals Vs minus Vf. So, V0 equals A into Vi. Now, A is Vs minus Vf. Sorry, Vi is Vs minus Vf, as I had shown you earlier in the PPT. Please recall that mixer network where we had a plus symbol and a minus symbol. Input voltage of the amplifier is the subtracted form of feedback voltage from the source input. So, AVS minus AVF, that is AVS minus, let us substitute for VF, that is VF is nothing but beta into V0. So, we get this equation 1 plus BA into V0 is equal to A into Vs, or in effect we get AF equals V0 by Vs equals A by 1 plus beta A. It is the same expression which I showed you in my PowerPoint slides. Now, this equation 14.2 shows that the gain with feedback is the amplifier gain reduced by a factor 1 plus beta into A. Now, the factor will be seen also to affect input and output impedance among the other circuit features. We will see that this 1 plus A beta is going to come again and again in all our future derivations. We will see that when we derive for input impedance also, we will see that when we derive it for output impedance also. We have already seen yesterday that with this negative feedback, input impedance is going to increase and output impedance is going to reduce. How that is going to happen, we will see that now. Now, similarly for the, just like we had a voltage series feedback, now we have a voltage shunt feedback. In the voltage shunt feedback, the gain with feedback for the network is AF equals V0 by Is, because at the input we visualize the current source, as I had mentioned yesterday. This V0 is now A into II, and Is is nothing but II plus If there, because it is a current there at the input side. Now, II plus If, it is A into II divided by II plus If is again beta into V0. The feedback current is nothing but the fraction beta into V0. So, now it is A into II divided by II plus beta into A into II. II is common, it will get cancelled, you will get the same expression. In fact, for all of those 4 feedback types or connections, you are going to get the same expression, that is AF equals A by 1 plus beta into A. Or when we generally keep on mentioning about it, we simply say AF equals A by 1 plus A beta. Either we mention beta into A or we mention A beta, because mentioning A beta is easier for us. So, for all the 4 types of connections, when you apply the same equations, you are going to get the same equation, AF equals A by 1 plus A beta. Okay. Anyway, my suggestion to you again is, don't just listen to me, don't just read this particular textbook. You will have to practice all these equations on your own by writing the block diagram for a particular type and actually writing an expression for the gain with feedback AF. Otherwise, now it all seems to be very easy for you because they are all having a similar nature. But unless you work out, you will not be able to remember them. So, please keep on practicing these derivations. These derivations are sure to come in the test also, they are sure to come in the external exam also. So let me proceed now. Let us see the derivation now for input impedance. Okay. So now input impedance with feedback. First let us see voltage series feedback. A more detailed voltage series feedback connection is shown in figure 4.3. That figure I will go back later. Now the input impedance can be determined as follows. II equals Vi by Zi. Input current is equal to input voltage by input impedance. Now Vi is nothing but Vs minus Vf divided by Zi, as you already recall the block diagram. Input voltage is signal from the source minus Vf because of the negative feedback. Now Vf is nothing but beta into V0, which you already know. So Vs minus beta into V0 divided by Zi. Or again, what is V0? V0 is equal to A into Vi. So now Vs minus beta into A into Vi divided by Zi, that is II. Now let us cross multiply. II into Zi is Vs minus beta into A into Vi, as you can see here. Now what is Vs? Vs is now the same equation. Let us rearrange. Vs equals II Zi plus beta into A into Vi. Or it is II into Zi plus beta into A into, what is Vi again? II into Zi. Okay, you can see this equation now. The input voltage Vs is II Zi plus beta A Vi. For Vi, we will substitute again II into Zi because V equal to I into Z. We already know voltage is equal to current into impedance. So II into Zi plus beta into A into II into Zi. Now let us find out the input impedance with feedback. Input impedance with feedback is Vs by II, because Vs is the signal coming from the source and II is the input current, as we have already seen. So Vs by II, all this II gets cancelled and we get Zi into 1 plus beta A. See, Zi into beta A into Zi, or Zi into 1 plus beta into A. Now look at this. Input impedance gets increased by a factor of 1 plus A beta, because it is a multiplication now. Input impedance with series feedback is seen to be the value of the input impedance without feedback multiplied by the factor of 1 plus A beta, and applies to both voltage series and current series configurations. It is applicable to all the series configurations now. We have two series configurations called voltage series and current series. Now whenever we have series configurations, input impedance is going to increase. Remember this factor. So whenever we want to have increased input impedance, we have to go for series feedback. Okay. Now I have been telling you this particular term 1 plus A beta is going to come again and again everywhere. It is going to come again in all our future derivations also. Now if A beta is much larger than 1, then what happens? If A beta is much larger than unity, we can ignore this 1. When we ignore this 1, what happens to the input impedance with feedback? It is going to be multiplied by a factor called A beta to the open loop input impedance. Zi is the open loop input impedance. A beta is called as the loop gain now, because it is with the feedback. So whenever we have a series feedback and negative feedback, then the input impedance will be increased by a factor of the loop gain or A beta. Now this is a distinct advantage. That's why yesterday I had told you, with the negative feedback, input impedance will be increasing, even though we are compromising in the voltage gain. I hope this is all understood. If you have any questions, you can always unmute and ask me, or you can use the chat box also for the questions. Otherwise, I will continue. Now you can see this network. This is the voltage series feedback network, where we have already derived AF equals A by 1 plus beta into A, or AF equals A by 1 plus A beta, where A beta is called as the loop gain. And you can see this ZIF is the input impedance with feedback, ZOF is the output impedance with feedback. Okay, based on this particular pictorial depiction only, we have derived the expression for input impedance. The more you see these diagrams, the more you will remember. Better is if you write these diagrams on your own, you will remember better. Because you can see here, what is this Zi? Let me annotate. Now this Zi is nothing but the input impedance without feedback, right? It is the open loop input impedance. What is Z0? Z0 is the output impedance without feedback, or it is called as open loop output impedance. That is what is depicted here or shown here in this figure. Now with feedback, we will have a different symbol called ZIF. And we already saw the expression for ZIF is Zi into 1 plus A beta. We will proceed with the expression for ZOF. But you will have to remember this diagram again for the next derivation as well. So let me proceed now. Now let us see for the voltage shunt feedback. The feedback connection is like this. See, Zi is already shown here, Z0 is already shown here, and the shunt feedback we have already seen, and the need for the current source also we have already seen. So I need not repeat it again and again. Let me proceed. Now for the voltage shunt feedback, again ZIF is VI by IS. Just see here, for the voltage shunt feedback, input impedance with feedback is now VI by IS, where it is the current source at the input. So now ZIF equals VI by IS, and IS is what? II plus IF. You can see here, I will show you the diagram now. IS is equal to II plus IF. Now you may think, yeah, we are applying negative feedback, right? So this arrow mark is like this. Yesterday I had answered the question. So II is going this side, IF is going this side to the feedback network. So the current from the signal source is the summation of current going as input to the amplifier and current going to the feedback network as well, because we are considering the current source at the input. So IS equals II plus IF. Now because of that, let us substitute VI by II plus IF. What is IF now? Beta into V naught. The feedback current is nothing but the fractional form of output voltage. So VI by II plus beta V naught, or now VI by II, let us divide throughout by II. II by II plus beta into V naught by II. Now what has happened at the top? The numerator VI by II is nothing but Zi. It is the input impedance with open loop. At the bottom, II gets cancelled. What is V naught by II? V naught by II is nothing but the gain of the amplifier, open loop gain of the amplifier. So now ZIF is equal to Zi divided by 1 plus beta into A. Now you can see here, what happened here? Here the input impedance got reduced by the same factor 1 plus A beta, because the factor 1 plus A beta is coming at the denominator. So what does this mean? Whenever we have shunt connections, the input impedance is going to be reduced. Now you may wonder, if the input impedance is going to be reduced, what is the use now? because ideally we want the input impedance to be increased. But I had mentioned in one of my earlier classes that we have a concept called impedance matching, where many times we will have to match the source impedance to the load impedance. In such cases, when we have a multi-stage network, we require some circuits which can match the impedance as well. So in this case now, in the case of shunt feedback, the input impedance is going to be reduced. So what we can do is, let us say we have to connect to an amplifier to some other circuit at the other side where impedance has to be matched. Let us say impedance is lesser. Now we can use such voltage shunt feedback or current shunt feedback also. Okay. Now this reduced input impedance applies to the voltage series connection of figure 4.2a, voltage shunt connection of figure 14.2b. Okay. Now I am discussing the voltage shunt feedback and we are discussing only the input impedance. Now you can see in the earlier case input impedance got increased. Now in the present case input impedance is going to be reduced by the same factor 1 plus A beta. Again, if A beta is larger than unity, we can as well directly say that the input impedance with the voltage shunt feedback is going to be reduced by a factor of the loop gain itself. Okay. So you can see now we have 4 types of connections: voltage series, voltage shunt, current series, current shunt. In all these 4 types, we will have different variations of input impedance as well as output impedance. Whereas the expression for the closed loop gain is going to be the same. AF will always remain A by 1 plus A beta. But ZIF will increase in 2 cases, ZIF will reduce in 2 cases. Similarly, ZOF also, the output impedance with feedback, that is also going to reduce in 2 cases, it is going to increase in 2 cases. Later on, I will show you a tabulation in my PowerPoint slide about in which type of connection we have which type of advantage, which type of disadvantage. And even now it may be seen that this input impedance is going to be reduced by a factor of the loop gain. This can also be useful when it comes to impedance matching. That is the idea here. So it is already time up now. In tomorrow's class, let me discuss about the output impedance with feedback. It is already there on this screen now, but let me not hurry up with the derivation of the output impedance. In tomorrow's class, let us see how output impedance is going to be affected in the negative feedback. Ideally, we want the output impedance to be reduced, right? It will be reduced in 2 cases, but it will be increased in the other 2 cases of the feedback. We will see that tomorrow. Later on, let me tabulate the whole outcomes of these 4 feedback connection types. Then you will get a complete picture about how these feedback connections are going to be useful in our electronic applications. If anybody has any connections, you can ask me now, or else I will conclude the class. Anybody has any questions? You can ask me. Okay, as there are no questions, let me end today's class. See you in the next class. Take care and goodbye.